Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at Amkor with Curtis Zwenger. We're going to talk today about the challenges of packaging 5G and 6G. Curtis, what sort of problems are you seeing in terms of packaging of 5G and 6G chips?
Predominantly just the additional integration needed to improve the signal integrity and power distribution networking for packages for the proper attenuation need for these high frequencies. It's a combination of package architecture, materials, and overall ability to simulate ahead of time and then ultimately test these structures.
Let's take a closer look.
Sure.
Curtis, what are we looking at?
Well, Ed, here we have a schematic of or side view of a antenna in package structure where you'll have the base substrate with the antenna layers, patch antenna layers embedded within the multi-layer organic substrate. Then you have the circuitry. This is the filters, step-down converters, the analog beamforming circuitry, etc. And then here we have the external connector, because this type of package is actually mounted along the bezel of the cell phone. So it's very narrow. The aspect ratio is quite high from a length and width standpoint. So it can fit along the edge of the bezel of the phone to give you that full 360 attenuation.
Most of the 5G today is sub 6G, and we expect that to finally change over to millimeter wave as we go to 5G, the next versions of 5G as well as 6G. How does that change what goes into the package and the package design itself?
It's all about reducing the insertion loss, crosstalk, and return loss in these structures as you propagate the signals and power distribution to the antenna arrays and back to the receiving circuitry. So it's all about integration. It's all about selecting the proper substrate materials. So you have the shortest trace and the ability to do impedance matching. Also have the ability to shorten the length of all the circuitry to the power distribution networking and also to the digital signaling. So it's really about having the shortest, lowest impedance path, the highest capacitance path to maintain that signal and power integrity. And that can be shown through the evolution of the additional AIP, AOP as we progress to support 5G and 6G type products.
And two of the problems that you deal with as you get into 5G and 6G millimeter wave are loss and drift, right?
Correct. Loss and drift are essential. And again, this is where simulation is key, the ability to understand the impact of all the materials, the dielectric constants, return loss characteristics, the ability to understand the design rules of the structure, the architecture you're proposing. So it's really a co-design effort between not only the circuit designers, but also the package designers. And so the EDA companies are now really putting a lot of emphasis on supporting design for 5G and 6G applications due to the reasons you mentioned for the drift and other aspects.
What kind of materials are you using in these packages, and does that affect how this functions?
Yeah, a number of different materials are being looked at, especially for the higher frequency applications. Currently, these type of substrates are standard BT coreless substrates buildup, anywhere from 14 layers, maybe 16 layers through the circuitry here. And then as we get into the next generation, which becomes actually, and I'll just simplify this design a bit, but they're actually extracting the patch antenna arrays and making them discrete patch antennas for a number of reasons. One is potentially to reduce costs by reducing the layer count within this high layer count BT substrate and put those lower cost layers in a 2-layer substrate here. And then also provides also more 360-degree propagation laterally as well as vertically for the antenna arrays themselves. So the antenna arrays are extracted, and this is called AOP. And then what this also provides is the ability to introduce different materials here as well. So BT has been the standard material. There's been talk about LTCC, low temperature coal-fired ceramics, to be part of the structure. There's some advantages there because definitely ceramics have some radiation properties, RF properties that are favorable. But that type of ceramic in our industry for consumer electronics are quite expensive and does not really fit the cost structure that we need for these type of products. Another potential material that's being used is looking at flexible type circuitry, and this is where LTCC is being used, which is another as an alternative to polyamide type of flex circuitry. So there's advantages to LTCC because it's much more shapeable, and so when you shape circuitry with a flex circuit, you're always concerned about any circuitry, any devices that are on that flex circuit to be damaged. Also, the the flex strength and the durability and reliability. So LTCC has very good properties as far as flexural stability and reliability over time. So that's being looked at. It also has very good characteristics regarding low decay and DF for RF applications. And then the next generation that we're looking at also for AIP is actually where the antenna layers itself are driving the form factor, because the circuitry is being further integrated and reduced size-wise to reduce cost of this circuit module. So now we have packages that we're developing is actually packaged on an antenna. So the package itself is not driving the body size of the structure, but it's the antenna array structure itself is driving the package size. So that's becoming where the integration of these DEM converters, analog beamforming circuitry, is being integrated into a smaller module, but it's the antenna array itself that's driving the overall structure.
So you've got a lot of options here. Is any one winning out, and for any specific reason? Cost, uniformity in terms of manufacturing?
Yes, as you know, in our industry, cost is king, so we're always looking at the lowest cost while maintaining or improving performance. So right now, this antenna on package seems to be the incumbent for the time being for 5G applications. We're seeing this package on module, we call it our package on antenna, I should say, or this is more of the third generation of the structure, where we can still use conventional BT substrates to keep the cost down by using heterogeneous integration techniques to integrate this circuitry in a more cost-effective and high-performance manner. So these three packages covers the 5G applications even out through mmWave. But as we get into the 6G 120 gigahertz plus applications, this is where the materials become even more important. So some of the structures that are being looked at from an architectural standpoint for 6G is actually RDL substrates, because RDL provides those fine feature sizes for very fine antenna design features. Also has very thin layer buildup in the dielectrics, which helps accommodate the higher frequencies, because you must have very thin dielectric between the base ground plane and the antenna layers themselves. So this is where RDL buildup is very beneficial, where you can have as thin as 10 microns separating those layers. And also for power distribution and networking, you can play around with the power and ground plane separations and locate them as close to the PCB circuitry as possible, so you don't have the effect of the ductance of the vias. So RDL type of wafer level processing is going to be taking playing a larger role for 6G applications, not only for the handset applications, but also for infrastructure for small cells, where they take essentially an AIP package that would be used for the cell phone, and in the base station, you tile these in a larger small cell situation.
So essentially what's happening here is that it used to be the package that would define where the antenna goes. Now the antenna is defining where the package goes, right?
That's correct. And now the antenna, because of the requirements of the antenna, are so tied to the frequencies that are needing to be supported, the antenna designs are becoming very critical. And there's a lot of different technologies that are being looked at, where you have very unique characteristics of surface characteristics of the antenna for improved beamforming, and also this is where RDL provides a nice advantage as well. Also, RDL allows one to match the impedance of the signal line. So if you're, for instance, on an AIP for a stack package, RDL processing with 3D copper pillar interconnects to the top DRAM package allows one to dial in the 50 ohm impedance to really improve the crosstalk, return loss, and insertion loss for those applications. So packaging, with all the things we have in our toolbox, is really coming into play now for advanced packaging, with 3D interconnects with copper pillars, also with the ability to use RDL for fine feature size line and space, and impedance matching, also layer control between the dielectric structures to improve signal integrity and power distribution networking. So it's a really exciting time to see how advanced packaging is starting to enable some of these advanced RF applications.
We're also starting to hear about some glass substrates, which are interesting. We've been talking about glass substrates for probably almost 15 years now. Why now? What does it bring to the table, and what are the problems?
Good question. Yes, glass is getting a lot of attention, and has for probably the past 8-10 years, even at our industry conferences, because clearly it has some of the best dielectric constant and return loss characteristics of any material other than diamond, for instance. So So it's very, very exciting because the glass industry has really put a lot of emphasis on not just providing standard glass that we see in our homes, but glass that has unique transmissibility characteristics, unique CTE characteristics that can help them be used as wafer carriers for our wafer 2.5D carrier industry. Also now for applications as an alternative for BT core or other type of cores that are being considered. So glass, it's cost effective. Uh, the challenges with glass is it's difficult to process with regard to via formation. It's various techniques can be used, and those are being optimized, and that supply chain is currently not well established, but is becoming so. Also, glass is very conducive to panel level packaging, especially for cord substrates. So panel level packaging is an exciting area that glass could play a large role. And the challenges continue though, since this is a new technology for packaging, is cost in the supply chain and bridging those gaps where we need to have a very high capacity ultimately and scale via formations, filling the vias, and then having good handling techniques so we don't have any damage during the assembly process.
One of the advantages of glass is it does have the same coefficient of thermal expansion as silicon, right?
Very close, yeah. Very well matches a lot of the silicon and more of the stiffer materials that we deal with in semiconductor industry. So the CT mismatches are addressed with glass compared to the organic core. So that's a very big advantage. Also, of course, the electrical characteristics and properties, and also the fine feature sizes that one can produce on glass using some of even the more traditional RDL type technologies. So glass has the ability to also have very highly integrated and fine distribution of signaling on the substrate itself. So it's very distinct advantages. I think we're also accustomed to dealing with organic laminates where we drill in our strips, we drill tooling holes, and the tooling holes are used to push the substrate through our assembly process. Now with glass, we have to come up with either carriers or some techniques to provide these extra features that accommodate a high volume manufacturing process. So that's some of the challenges I think the industry is facing now.
How about materials in the supply chain? Over the past several years, we've seen some serious problems in terms of delivering various materials through the supply chain. Is that starting to influence what gets used?
It had to a large degree during the pandemic where substrates were in a very severe shortage and lead times were just almost 10x is what they were pre-pandemic on some of the cord substrates. So so I think supply chain availability definitely dictates what will be used for advanced packaging and the time horizon when these materials will be needed. So when you're looking at something like 5G, those type of products need to be introduced within the next couple of years. But we're looking at 6G, where I think standards aren't expected till 2026 at the earliest, and even be 28 for any products to even be conceived. So those type of materials, material suppliers are actually developing to meet the needs of these low DK, low DF requirements. But just to address the supply chain in general, I think what we've learned from the past is we can't just base our forecasts on our customers' forecasts, but we have to base on our customers' forecasts, and that relationship with your supply chain partners needs to be from the top down. And now with the advent of AI and all the sensing techniques for RFIDs, I think the industry is really trying to understand how now to develop these strategic partnerships with your supplier and not just more of an adversarial partnership with your first line of supplies. So now I think we understand the urgency and the need that we have full supply chain partnership and contingency plans to, if we see a lead time that's being affected, we can react accordingly.
As we get into some of these advanced designs with all these complex antennas, how are we going to test them? How does that change?
Now with this highly integration of all this circuitry and advanced packaging heterogeneous integration, there's really no area for probe points for external conductors. So this is where over-the-air testing is going to be critical, and that's an area where I believe there's a gap as far as standards. So the over-the-air testing, there's not a lot of people that do that, and so currently that's outsourced to a large degree to either academia or companies that have the very sophisticated equipment for over-the-air testing and the chambers, et cetera, and the expertise to do so. And the other challenge is once these 5G, 6G application becomes more proliferated, that technology and that platform for over-the-air testing needs to be able to scale, along with all the ATE and other type of testing. So it has to scale in a fast manner too, because with the adoption rates that are expected, testing is going to be critical.
What are they actually looking for when they do test? Is it the quality of the signal? Is it the fact that all the circuits are running, or is it all the above?
It's all the above for sure. There's so many things that come into effect with these frequencies now that we're talking for 6G, 110 gigahertz plus, even up towards 300 gigahertz, and they're even saying terahertz at some time. So how that's affecting the infrastructure as well. They're going to need many more small cell sites throughout, especially in high density areas. And so trying to simulate that and test that to make sure we have a high quality network that's reliable, especially as ADAS becomes into play and you're relying on these high speed, low latency networks to make real time decisions on automotive driving and safety. So that's going to be critical. So testing, simulation and then test, that's I think an area where people are very concerned about, and making sure we have the ability to ensure that that framework and that infrastructure is reliable. So,
Curtis Zwenger, thanks for a great explanation.
you're welcome, and thank you.